Hello, I'm Professor Simon Tett and I'm the Chair of Earth System Dynamics at the University of Edinburgh. This short talk is about three things. First of all, it's about the rainfall on the island of Socotra and aims to describe the climatology. Secondly, the role of tropical cyclones and tropical storms in rainfall on the island. And finally, two cyclones and their rainfall impact on the island in May 2018. The work I'm describing is funded by the UK Research and Innovation Arts and Humanities Research Council for a project called Mitigating Climate Change Effects Through Traditional Land Management Practices. So to sort of provide some introduction for those who might not know, these images are all taken from Wikipedia. Here is a map of Africa and the Mediterranean, and this box here shows roughly where Socotra is, which is zoomed up in here. You can see here's Somalia, and here's here's the Arabian Peninsula, the Red Sea, the Gulf of Aden, and here into the Indian Ocean. And here, zooming in, so here's the north is the Arabian Peninsula. This is Oman. Yemen is just about here and to the west. And here's the Somali Peninsula, divided up into various countries at the moment. Socotra is an island. It's about 100 kilometers long out in the Indian Ocean, and it's part of Yemen. What's unique about it is it has this rather unique fauna and flora, with many species that only exist on the island. So here's a blow up of the topography of the island, and you can see that the highest peak is in the eastern side. This is about 1,500 meters. It does have a little airport down on the coast here. There's some lowlands on the north coast and on the south coast. We have some quite high topography on the southern end, and what looks like probably water channels, rivers where water flows down some occasionally. Though on the whole, as you can see from this satellite image from Landsat, it's a fairly dry island. And we'll see when we look at the rainfall, the average rainfall in the year is order 150 millimeters or so. If you look more carefully, you can see these kind of patches of darker material, and that's where there's more substantial vegetation. And one of the reasons for the project is to investigate how climate change might be affecting this island and how local management practices might be able to deal with that. So here's the climatological precipitation for the island. This data is taken from the ERA 5, which is a reanalysis. Reanalysis is a combination of a weather forecast model and data. So to be a little bit careful, particularly for rainfall, and one of the things we're going to do a bit later in the project is evaluate this against both the rather sparse local measurements and local knowledge. But the main thing to see here is we have got sort of two peaks in the rainfall. So we have about 35 millimeters a month in mid-May, and a peak in October, though a much broader peak ranging from, say, September through to December. And we have some months where we get almost no rain at all, 1 millimeter or so a month. To put that in context, average rainfall over the UK is about 3 millimeters a day. On average, it's about 168 millimeters a year. And we'll break this up a little bit. If you look below, you can see what's called the anomalous rainfall for each month. That's the difference from normal climatology. So more, if it's above the line, it's more. If it's below the line, it's less. This plus or minus 50 shows plus or minus 30% or so of the rainfall, of the normal rainfall, so fairly broad. Things that might stand out to you is this big black line here when we have more than 200 millimeters more than normal in 1 month. That would be May 2018. The green line show the 12-month running average, sort of relevant to water storage. So one thing that you sort of pick up from here is that the climate's become a bit wetter, but you can get these wet and dry periods. So for example, here in the late 80s, early 90s, or in the early part of the 2000s, it's drier than normal, while here in the most recent 5-year period or so, it's wetter than normal. And we'll see in a while, actually, that most of this is because of tropical cyclones, which it's worth stressing are rare events. So we can count the number of tropical cyclones. There's a lovely database of tropical cyclones. This is looking at the West Indian Ocean. Here is the Arabian Peninsula. Here's Somalia. Here is Red Sea, Gulf of Aden, Indian Ocean, India over here. So what's shown is in roughly 2.5 by 2.5 degree hexagons is the total number of 3-hour periods in which a tropical cyclone or tropical storm was present in this for roughly 40 years. So you can see they're quite rare. So for example, the peak point here is somewhat over 75, so maybe 2 or 3 a year. While here in the region around our island, Socotra, it's quite small, maybe 10 to 20. Occasionally, so a bit higher around it, but they're quite rare events. We wouldn't expect to see. We'd expect to see a tropical cyclone maybe once every 1 to 2 years, once or twice a decade in the neighbourhood of Socotra. That's essentially what this is telling us. And then I've also plotted on top of that the tracks of any tropical cyclone. So tropical storms are smaller scale disturbances. You have quite significant winds, but tropical cyclones are larger and more impactful. And you can see there's basically been 4 events. So this one here, Mekanu Sagar, is actually really 2. A cyclone that does this generates a rather small disturbance, which is hard to see, which then generates another storm here, which amplifies and crosses into a man, reaching a peak 3. The number in bracket shows the maximum intensity on the Schaefer-Simpson hurricane scale. So 3 is pretty large, 4 is extremely large. That was the largest one, Chapala. And up here, the key is showing the dates. And you'll notice the dates are all in 2015 or 2018. So we have essentially 3 events in 2018, though 2 of them are combined. Mekunu Sagar in 2018, which peaked at Storm Force 3, Luban, which was a Storm Force 2, these are the events that the cyclones that come close to our island of Socotra, and then we had another couple in 2015. So apart from that, there's been no tropical cyclones in this whole period. So the 2010s period is a period of unusual activity with 4 or 5, depending on how you count them, tropical cyclones in that period. So I'm going to define a tropical cyclone on tropical storm day. So we have a working definition. So I define a day as 2 conditions, both of which must be true. Having a tropical cyclone or tropical storm within 500 kilometers of the center of Socotra sometime during the day. So in any 24-hour period, any calendar period. And also having more than 1 millimeter of rain on average over the island. So we think about the average rainfall over the island, it must be more than a millimeter, and there must be a tropical cyclone or tropical storm within 500 kilometers. And I use this definition to classify days as either tropical cyclone, tropical storm, or normal. And then the analysis I'm now going to show is going to split that up. So worth remembering, average rainfall in a year is about 170. So if we partition it, so let's start with the annual precipitation here. So the annual precipitation on non-tropical cyclone years, or over days, averaged over the 39 years in the data that I'm looking at, is about 150 millimeters per year. And then over the 10 years of tropical cyclones, it's 62 millimeters or so. So you can see that's a fairly substantial, when you have a tropical cyclone or tropical storm, that's quite a substantial contribution. You can see they're rare. We've got 1 in 1984. We have a few isolated incidents here in 97, so that's only a one day or so, or a little bit of rain, so it probably wasn't a very impactful event. Maybe the storm didn't come that close or didn't produce very much rainfall in the bit where it crossed Socotra. In 2004, then we have quite a large amount of rain in 2010, and again in 2015 and 2018 and 2019. So there's a sense that these things are becoming larger. If we look at the annual maximum precipitation, which you might think of sort of most heavy rainfall in a year, the clear thing that stands out is in generally, not always, so for example in 2019 or 1994, we have very high maximal annual rain days associated with tropical cyclones, within a couple of cases well over 100 millimeters. So that is likely to have quite a big intensity. If we look at the rain days, then the average number of days with rain, so how many days a year with 1 millimeter of rain or more, is on average around about 40, 37 or so, while for tropical cyclones or tropical storms on the years we have them, so the 10 years of which there are some, it's about 2.6. I'm also showing the coefficient of variation to give you a sense of how much variation is there. So you can see there's quite large tropical cyclones or tropical storms have much larger variation than say normal days. Normal days, they're plus or minus 30%, which I was sort of using earlier, while tropical cyclones, tropical storms are of much larger variation. And the rainfall intensity, which is essentially the average rainfall on rain days. So for normal conditions, it's about 3. So when we get rain in Socotra, it's on average about 3 millimeters a day. While if we have a hurricane or a tropical cyclone or a tropical storm, we have about 18 millimeters per day, and again, much larger variations. Intriguingly, the variation in intensity and the variation in rainfall days is quite similar, but actually the variation in rain days is a little bit less. So it suggests that rainfall changes on normal days is a large component, largely, but not entirely, but half and half actually driven by changes in intensity and changes in the number of rain days. I now look at the partitioning of rainfall into rain from non-tropical cyclone conditions, or non-tropical cyclone and non-tropical storm conditions, normal, and tropical cyclone conditions as a function of time of year. So I'm going to look at the total rain and the number of rain days. So remember, a rain day is rainfall more than a millimeter. So the left plot here shows the rainfall, total rainfall in millimeters. This is the average over the whole 39-year period. It's worth remembering that only in about 10 years do we actually have tropical cyclones. So these contributions are averaged over the whole 4 years. In years in which we have a tropical cyclone, they will contribute considerably more. And what we can see is we do have our hard and wet periods, as we saw before, are in May, and then the sort of with slight amounts of rain, a few millimeters in April and May, and then a sort of another wet period where we get like 35 millimeters or so in October, with maybe the start of that in September and its end in December, January, depending on whether you think 7 millimeters or not is a lot of rain. And what we can see is that tropical cyclones in the past 40 years have really have made a substantial contribution to the total rain in May, and relatively small contributions in October, November, December, though the total here is not terribly dissimilar from that. And given how rare these events are, there's just maybe chance. We look at the actual average number of rain days. So we can see again the rainfall looks like it's basically the intensity is about the same throughout the seasonal cycle, but the tropical cyclones, tropical storms are on average quite small number of days, hardly any, contributing quite a lot of rain, and similarly in October, November, December. So I think the summary of all of this is that rainfall, tropical cyclones, tropical storms, are rare, but contribute quite a lot to the rainfall. So, sort of conclusions and future questions. Socotra is quite dry, that's what we've seen so far. A substantial fraction, especially the May precipitation, comes from rare tropical cyclones and tropical storms. They're very rare, but they bring quite a lot of rain, or have brought quite a lot of rain, especially in May. And the extremes in wet daily and annual precipitation appear to come from tropical cyclones and tropical storms. So if we see a very wet year or a very extreme event, it's likely to have been a tropical cyclone or tropical storm that did it. There appears to be a shift in the 2010s with 4 to 5, depending on how we count them, and we'll see that in a minute when we see the animation, with 4 to 5 tropical cyclones near Socotra, while prior to the 2010s there were only tropical storms, and in fact there's really only the event in 1980 in the mid-80s. So what we've seen is the 2010s are much wetter than the previous period, so I think that's largely due to a larger number of tropical cyclones and tropical storms coming close to Socotra. However, there's some issues. How reliable is the uniform precipitation, on which all this analysis is based on? And one of the things we want to do, or I think we should do, is compare this with both local knowledge and with the very limited observations there are. It also, I think, is worth questioning our locals, seeing what local knowledge has to say about tropical cyclones and tropical storms. I think they probably will be some knowledge of what's happened in the past, and I think that's definitely worth pulling out. And then I think one big question, possibly not for the project, but beyond the project, is what is the cause of tropical cyclone increase in this part of the Indian Ocean? Is it climate variability or is it climate change? One thing we do expect from sort of existing knowledge about tropical cyclones and tropical storms is we expect that precipitation will become larger in response to warmer conditions. We'd expect it to become more extreme, possibly more concentrated, which may mean effectively that there's more variability in the impact of tropical cyclones and tropical storms on Socotra, depending on whether it got the wet bit of the storm or not. So I think it's worth thinking about a more significant partitioning of the changing rainfall into intensity in days to see if there's any evidence. I mean, it certainly looks like from 2015 and 2018 events or years that it was more intense. We saw that earlier. So going on, I'm now going to show an animation of the May 2015 tropical cyclone, tropical storms. That's when we have two events or two tropical cyclones or storms near Socotra. And this is what we're about to see. I'm going to talk you through essentially the animation, or how the animation is constructed that you're about to see. So what's shown, there's two plots, and the top plot is the current timestamp. That matches the star in the bottom plot. So the star here shows where you are. If you want the exact date, it's up here. So this is 2000. This is the 22nd of May 2018 at 22Z. Z means essentially the time, the universal time, which is measured at Greenwich. To get the local solar time, depending on quite where you are, add about 3 degrees at 4 degrees. So add 3 hours or 4. So add about 3.5 hours to the time to get the local solar time. I don't know offhand what the local time is in Socotra. I imagine it's on Yemen time, so it's plus 3 hours, I suspect. Okay, so the colors here, so you can see the geography. So here's the Arabian Peninsula at the top, here's Somalia, there's Ethiopian highlands around here, here's India over there, and so we're in the Arabian Sea, here's the Red Sea heading up here, here's the Gulf of Aden, here's the Persian Gulf there. So the colors show precipitation. Note the scale is logarithmic, so it actually doubles, 0.51 to 4, 8, 16, 32, so above 32 is yellow, so there's a patch of quite intense rainfall there. That's millimeters per hour. The red lines show our contours of pressure every 4 hectopascals, and then the purple lines with arrows are the stream flow. Stream flow is the trajectory that a tracer, so something that doesn't affect the circulation, would make if that circulation was continued indefinitely. Of course, the circulation changes. The thicker the lines are, the stronger the winds are, just to give you some idea on the arrow show. So you can see, for example, here we have on the 22nd of May, here's a tropical a storm beginning to develop. I'll explain the numbers in a bit, but you can see off the southwestern flank these strong winds flowing into it. And actually spiraling in, crossing the contour lines. And then you can also see flow out, so to the south of it, for example. Some quite weak flow coming into the north. The inset here is a blow-up of this region here, centered on Socotra. That's the white star. And you can have the same, everything is the same. So pressure, contours, and colors are the same as is the geography line. So there's Socotra there. Here's the coast of Somalia, corresponding to this little region here. It's in slightly greater resolution, so you can see the rest of the archipelago, these 3 small islands, compared to the large island itself. And the only difference is that the stream function arrows are well, they draw the same density in this corner as they are here, but that just means there are more of them, so you can see more. And for example, here you can see actually the islands inducing, at least as far as the ECMWF reanalysis is concerned, and that's where I should say where the data comes from, a circulation around it. As the wind gets drawn around it, it's generating some flow around here and into the cyclone. You can see very clearly the spiraling in. These are winds at 950 hectopascals, so just above the surface. I've chosen that because that takes us just above the top of Socotra as we come near the well, at least as ECMWF reanalysis sees it, because it averages over about 25 kilometers or so. I think that covers all the features in this plot. There you're going to see in the animation every hour. Oh yes, one thing that's missing, the dashed lines here show political boundaries. So here's Yemen, here's Oman, here's the United Arab Emirates, there's Saudi Arabia, here's the 2 Somalia and Somaliland, Djibouti, Eritrea, Ethiopia, and South Sudan here as sort of major things. Below is a time series of hourly rainfall in millimeters per hour at this star point. And as I already said, the black star shows where we are. The other feature I didn't talk about on there is showing the passage of the cyclone. There's two of them. So there's one here, and then there's one that tracks here. Black is in the past, grey is the future track, and the number here shows the strength of the cyclone every 12 hours on the Schaefer-Simpson hurricane scale. So it's really a measure of the wind strength. So Cat 1s are the sort of weakest tropical cyclones. Cat 0 are tropical storms. So this was largely a tropical storm, deepened a bit here to form a tropical cyclone, and then travels through. On this inset map, the only difference is that the tropical cyclone, the strength of the storm is shown every 6 hours, so somewhat more densely. Okay, that's an overview of what you're about to see. Now just watch it. I will talk over the animation and try and provide a bit more detail. The animation plays twice, once fairly rapidly at about a second a day, and then a next at about 6 seconds a day. So you get a sense, you can see what's happening, and there's some features you'll see before this gets going is the daily, you'll see a little daily cyclone pressure, much of which is actually caused by the atmospheric tide. That's a semi-diurnal, so that's a twice a day cycle caused by solar heating. But there's also, if you look more carefully, a little bit of a land sea effect too. So you can see intermediate, occasional rainfall here. See the diurnal cycle, that kind of breathing in and out, but not much else happening. And up comes a little pulse of rain, and then you'll see the first tropical cyclone develop. That's it, here it goes, and then it passes down the Gulf of Aden, bringing rainfall. And then we can see the next one spinning up, and here we go, straight past Socotra into Oman. And then we're back to conditions. You can just about see the small. Now we're going to play the video a bit more, the animation more slowly, roughly a second every 4 days. Here's the towards Socotra in the inset. You can see the way the circulation changes throughout the day and how the pressure changes throughout the day. Those are a combination of the semi-diurnal tide and the land sea contrast, probably largely from Saudi. Other things you can see is rather intermittent precipitation over the highlands of Ethiopia and out in the Indian Ocean, and little bits of rain being generated off the coast of Somaliland. But Socotra is dry, but now we're about to spin up the first cyclone, so keep an eye on both the inset and the main map. You can see the rain coming along, and actually the rain exists before the cyclone does, and now the cyclone's a clear feature propagating down the Gulf of Aden, but there's rainfall happening behind it in little waves, and then we see it kind of reaching Djibouti and penetrating into Ethiopia and Eritrea, leaving not much. And now we're spinning up the second cyclone, and that's much stronger. You can see how low the pressure is. It's still a tropical storm, and now it grows to stage 1, and it will just be 2 and 3 as it hits the coast of Oman and then penetrates into Oman and Saudi Arabia. Socotra is dry, and then not much else happens, but you can sort of see there, you can see the wind over the Indian Ocean. That's the monsoon, the southwest monsoon, which is an important part of the climatology of Socotra. And I hope you enjoyed the video. Here is the accumulated precipitation and the storm. So we can see the two storms. One here, this one at -3 is when it's pretty weak, tracked like this. And actually then we see little dots of it tracking all the way to form this little feature, and then it tracked here. It peaked at, I think, at about 3. It peaks at about storm force 3 just before it hit the coast of Oman. And so that's quite severe. You can see the winds, which essentially are often the trade winds, the monsoonal circulation, though a bit of an adverse. But you can see some very heavy rain is essentially both systems track. So one tracks down the Gulf of Aden, starting here just off the coast, bringing some rain, corresponding to that little pulse there, and then bringing a lot of rain into Djibouti. But you'll see how narrow it is. I mean, there are regions of Somaliland get no precipitation at all on this map. Note the scale is still logarithmic, but starts at 50 and goes to 2,000 millimeters. And remember, annual precipitation in this area is order 100, 200 millimeters. So this is a substantial amount of rain. There's Socotra on the gradient. on the edge, so getting somewhere between, depending on where we are, 500 to 200 millimeters extra rainfall, and even into the interior of Saudi, that brings some significant amounts of rainfall. And I'd like to acknowledge where the data comes from. So the data came from the ERA 5 reanalysis. You can get it at this website, www.wf and forecast datasets reanalysis, datasets ERA 5. And the tropical cyclone, tropical storm data tracks comes from the International Best Track Archive for Climate Stewardship, IB tracks. I process the data using Python with the X-Ray and Pandas modules. I recommend both. I visualized it using Python with Matplotlib, and the work was funded by UK Research and Innovation, mitigating climate change effects through traditional land management practice.